Good evening, all. Welcome to the week 9 problem solving session for the course Matlab-Based Programming Lab in Chemical Engineering. Let's wait for like few more minutes so to see just if there are more students to join the session, and then we'll start today's class. So let's start today's session. So this week's problem that we are trying to solve is of a porous spherical pellet catalyst. So let us go through the problem once and then we'll discuss what kind of problem it is, and then I'll show you a few examples. And then we'll come back to this problems because this problem has several sub questions. So I feel like if you are able to understand like how to tackle this kind of a problem, then the sub questions will become much more easy. So here, consider a porous spherical pellet of a catalyst in which only radial diffusion of the reactant and the product. Just a second. So first, let us discuss the problem. I'll just give you a quick understanding of what kind of problem it is, and then we'll try to see how MATLAB is solving this kind of problems. Okay. So consider a porous spherical catalyst in which only radial diffusion of reactant and product is assumed. The reaction is a first order reaction of the type A giving B, and the schematic of the system is shown below. So here you can see it's a spherical catalyst and it is porous, which means the materials that are deposited, or if there are materials deposited on the surface of the catalyst, it will has the capacity to diffuse into the catalyst. Okay, so here only not only diffusion, there is one more thing that is happening. That is, there is an element A which is on the surface of the catalyst. The element A can diffuse into the catalyst. That is one thing, and also the element A can get converted to the product B because this pellet can act as a catalyst for this reaction. So there are two kinds of phenomenon that is happening. That is diffusion and the reaction that is happening, and the reaction is of a first order reaction. So there are certain conditions that are given to us. So here, for example, here we are considering this is the point where, just a second. So here we are considering this is the center of the catalyst. At the center of the catalyst, we are considering R, which is the radius is equal to 0. And we are taking that the concentration of A is 0 to begin with. So that is at time t equal to 0, which means when the process has started, we are assuming that the concentration of Ca is 0 at R equal to 0. And this is surface of the catalyst where the small r is equal to capital R. So capital R is the radius of this catalyst pellet. Okay. So when R is equal to 0, that is the center of the catalyst, at the beginning of the process, at T equal to 0, concentration of A is equal to 0. That is the one condition that is given to us. And again, at t equal to 0, which means at the beginning of the reaction, and when R is equal to capital R, that is at the surface of the catalyst also, Ca is equal to 0. So to begin with, we are assuming that at time t equal to 0, there is no Ca at all, like throughout the catalyst. That is, even inside the catalyst or even at the surface of the catalyst, we don't have concentration of A. Now what happens is, now we are telling that as the time progresses, it could be any time. What happens then? As the time progresses at R equal to 0, that is, when the center of the sphere or the center of the spherical catalyst, we are considering Ca is again 0. At some time t, Ca at the center of the catalyst is 0. Okay. And at some time t, at the surface of the catalyst, that is R is equal to R, the concentration of Ca on the surface is given by a new value, that is CaS. So CaS is a new constant value. Okay. So these are the conditions that are given to us. So now what kind of problem it is? So this kind of problem, when we have to model both the diffusion part and the reaction part, then finally you get a ODE equation. Sorry, we get a differential equation like this. So here what we have is we have a concentration Ca that is varying with respect to time, and also R here refers to the radius of the sphere. Okay. So we have here Ca that is varying with respect to time and the radius of the catalyst. And here this account D accounts for the diffusion coefficient, and Kca accounts for the first order reaction. So if you have a second order reaction, you have to change this part accordingly. So here we have a first order reaction, and here diffusion is happening. So now what kind of problem is this? So earlier we have seen ordinary differential equations, and we saw two kinds of ordinary differential equation, ordinary differential equation initial value problems, and we saw ordinary differential equation boundary value problems. But fundamentally in ODE, what we observed is that there is only one independent variable. For example, it could be the position. Like for example, last time we did how the temperature is varying along the length of the road. So the length of the road that becomes the independent variable there. And before that, we saw how the temperature is diffusing as time progresses. So time is the independent variable there. So for ordinary differential equation, you had just one independent variable. The independent variable means what comes in the denominator of d by dt part. We only had one such variable to deal with. But here what we have is you have Ca that is varying with time, and here Ca which is varying with the radius of the catalyst pellet. So there are two independent variables here, that is time and the radius, and hence it becomes partial differential equation. So that is why you see dou by dou t instead of d by dt, because it's a partial equation. Ca is a function of both your time and your radius. So that's what this equation tells us. So this is a problem that we need to solve. So this week we'll be trying to solve partial differential equations given so many boundary conditions, and we have certain constants also that we have to deal with. So coming to the constants, you have the diffusion coefficient, which is given as 0.15 centimeter square by second inverse. And we have K, which is the rate of the reaction, which is given as 0.1 meter inverse. So here you have to observe one thing. Here the unit of time is in seconds. Here the unit of time is in minutes. So it's better that you convert this to seconds so that you don't have any error while calculating your values. Next is CAS. That is, as I said earlier, at any time when R is equal to R, that is at the surface of the catalyst, we said that the concentration of Ca will be some constant value. What is that constant value? So the constant value is supposed to be 120 millimole per meter cube. So this is a constant value that is supposed to be. Now, what is the radius of the catalyst? That is the next important variable that we have. So that is radius of the catalyst, that is capital R, is nothing but 2 centimeter. So these are the informations that are given to us, and we need to try to solve this problem. Do you have any questions about how this problem is formulated? Okay. Now let us move forward. So, so before that, let me just go through what are the problem statements that we'll be dealing with today. First is test the temporal variation of the concentration profile in the catalyst pair. So there are two things, okay? Temporal variation means how is it changing with respect to time, okay? So temporal variation of concentration profile. So concentration profile, you have to basically see how the concentration is varying with respect to time in the catalyst pellet. Now, determine the effect of the diffusion coefficient, that is D, and the rate constant, that is K, on the concentration profiles. So such kind of problems we have done before. That is what do you do? You're anyway, the first part of the question you would have done with a constant diffusion coefficient and a constant rate constant, right? So when you come to the second part where we have to study the effect of this diffusion coefficient and rate constant, what do? You loop over several values of diffusion coefficient then you keep the rate constant fixed. Or else what you do is you keep the rate constant changing as per a loop and diffusion coefficient will be kept fixed. And then you will evaluate the same thing inside the loop, like the temporal variation, the same thing you run inside the loop. Or else what you can do is you can change both. You can change both diffusion coefficient and rate constant together. And you can take various parameters and understand how it is varying. So these are the things you could do. Now, access whether the part of the pellet remains unutilized at some values of these parameters. So we need to understand if some of the part of this pellet will be remaining unutilized or not, which means will the pellet be diffusing completely inside the pellet? Because what happens is, as you know, this is a first order reaction that is happening. So there are two kinds of things that is happening here. That is diffusion and the reaction that is happening here. So what if the diffusion coefficient, that is the ability to diffuse of this element A, is very less compared to the reaction rate constant? So that could possibly happen. Then what happens is the A might be slowly diffusing here, but you will see that A is very fastly converting into B. So then there will be zero A at the center. Okay. So basically this region will be unutilized because A is not reaching there. Okay, so some part of the catalyst may remain unutilized depending on what is your rate constant and what is your diffusion constant. Okay. Now, study the effect of time and space discretization on the time requirement for the solution of the problem. So there are several things that you can study. One is the space and time discretization. That will come into another thing. Now, small the problems for spherical coordinate system. Compare the contrast differences qualitatively as well as quantitatively. So these are the things that we need to address this time. So before that, let us come into how to solve. So before coming into the specific question, we'll see how to solve a partial differential equation. So for that, there are certain things that you need to identify in the problem before formulating it. So first is the model equation itself. So the model equation, you know, that is dou Ca by dou T is equal to d dou square Ca by dou R square minus Kca. This is a partial differential equation that we are dealing with right now. Now, the next is the initial condition. So what all condition do you need? So one thing that you have to observe is that you can see with respect to time, it is a first order. That is, there is only dou by dou. It is not dou square by dou. So it's only a first order derivative, not a second order derivative. So in that case, you need just one condition. So if in time, if it is just first order derivative given so according to that, which first order means the power is equal to one. Okay. When the power is one, what do? Then you need one condition with respect to time, what is happening. Okay, that is called the initial condition. When you look at the position coordinate, there is dou square by dou r square. Okay, this is the second order. So what do? The second order, what you'd have is you need two conditions. And with respect to position, what do you say? When you have two conditions, it is said to be boundary conditions. That is, you have it one position, you have one value, and the other position, you have two other values. So it is called as a boundary condition that is given. So what is the initial condition? What are the two boundary conditions that are given to us? So let's come to that. So initial condition means what happens to the system at the starting of the process. And when does that happen? That happens when time t equal to 0. Okay, so here basically if you can see this is t and this is r. So when time t equal to 0 and whatever the radius is, we are saying that the concentration of Ca is equal to 0. So that we have seen in the previous slide also. Whatever position it is, at time t equal to 0, we are considering that even inside the pellet or on the surface of the pellet, the concentration of A is 0. Next is coming into the boundary condition. What are the boundary conditions? We are telling that at whatever time it be, at position R equal to 0, that is inside the catalyst, the concentration of A is 0. So inside the catalyst, we are assuming that at whatever time we take, inside the catalyst, the concentration of A is 0. But at any time, but R, that is the position is equal to the surface of the catalyst pellet, we are considering the concentration of Ca is equal to 120 millimole per minute, whatever it is. Okay. So these are the two boundary conditions. So this is called as an initial value condition because this tells what happens to the initial condition of the system. Next is we have two boundary conditions. One is for position r equal to 0, that is inside the catalyst pellet. Another is for r is equal to r, which is the outside the catalyst pellet. So this forms one initial conditions and two boundary conditions. Like if we have a different function, what if it was just dou Ca by dou r? Okay, not a second degree. And what happens is you only require one position conditions. Okay, you need not require boundary conditions. You just require what happens at one single position to solve this problem. Now, other thing is, what do you call this kind of problem? So this kind of problem is called as second order first degree partial differential equation. So what is second order first degree partial differential equation? So coming into that second order means you have dou by dou, which is first order. Then you have dou square by dou r square, which is second order, right? The power is equal to 2. So when imagine you have like several dou by dou terms here. Among that, which is having the highest order. Order means the power of this dou. So the highest power is 2. So this is the highest power. So hence, sorry. Okay. So the highest power is this. So hence it is called a second order. Okay. Hence it is called a second. It's called a second order. Now, what is first degree? First degree means whatever the highest power is, we see what is the exponential term. So that is here you can see this. Sorry, just a second. Let me just erase it. So here you can see this term. Here again, this term, the whole term's power is just 1. Okay. What you can have is you can have square also. Like, sorry, this is today. So some problem with the writing. Yeah. You can have 2 also for this whole term. That can also happen. In that case, the degree becomes 2. So here what happens is you only have a power. The whole power of this term is just 1. So hence it's called as first degree. But what is order? Order refers to the power of dou term. So this is a second order because the power is equal to 2. First degree because the whole term is only having an exponential term of 1. So it is called a second order first degree partial differential equation. Is that clear? Just a second. So before coming into this particular question, let me just give you what are the basic understanding of PDEs, and then we'll see how MATLAB is trying to solve such PDEs. Okay, and then we'll come back to the question then because it will be more easy for you to understand how the question has been implemented in MATLAB. So coming into the first portion, we have two kinds of equation, that is ODEs and PDEs, which I have said earlier. What is ODEs? ODEs depend upon a single independent variable. That is, it could be either it could be time dependent or it could be position dependent. It could be also the position could be in Cartesian coordinates. It could be in the it could be in the just in the r direction, whatever it is. So there is only one single independent variable, and then it is called as the ODE equation, ordinary differential equation. And it also has two kinds, which is a initial value problem and another is a boundary value problem. Another thing is PDEs. PDEs is two or more independent variables. For example, whatever we saw here, we saw the concentration of A is a function of both time and radius. So there are two independent variables here, which is the time and the radius, and hence it is called as a partial differential equation. So there are some examples given here. Please try to understand if you can differentiate between ODE and PDE. So the first question is a road conduction. The road conduction, you know, what's the temperature? Dou square T by D square T by dz square is equal to gamma T minus TA. Here the time is only dependent upon the position coordinate set. Hence, we can say that this is an ordinary differential equation. Okay, now coming to the other case. So what is this? This is a steady state road conduction. That is, we are telling that the time, dependence of the temperature on time, it is basically on steady state. That is dt by dt. That is with respect to time is equal to 0. That is why we say the system is in steady state. What if the same road conduction problem was in transient condition? Transient condition means the temperature is varying both with respect to position and also with respect to time. That is called as a transient condition. That is dou t by dou t. So you can see it is varying with respect to time is equal to alpha dou square t by dou z square, where z is a position, minus beta times t minus ta. So here you can see we have two independent variables here. We have two independent variables, that is the time and the set. So here we can say that this is a partial differential equation. We have both here position set and time as a independent variables, and your dependent variable is your temperature. Now the same thing, you can come to the road conduction problem for a plate. So for a plate, what happens? So the plate will be like this, a square plate. Okay. So there could be heat conduction in this direction and heat conduction in this direction. Okay. So there is two-way conduction that is happening. So you can see dou square T by dou x square and dou square T by dou z square. Where this you can see is x and this is nothing but z. Okay. So here temperature is varying along the x-axis and temperature is varying along z-axis. But in both the cases, you can see time is dependent upon two position coordinates, z and x. Two positions. Earlier we saw time and position, but here both are positions, but positions along two different directions. In that case also, what we have is a partial differential equation. Okay, so here the dependent variable is temperature and the independent variable is the position along the x direction, position along the z direction. There are two independent variables that are there. So this kind of problem is also called as a partial differential equation. Now moving forward, we need to understand what kind of partial differential equation that we have. So if we are given second order PD, what is second order PD? Second order PD means you should have this dou square by dou z square. That is the highest power should be 2. So that is what we have said, that is said that by second order PDE. So imagine that you have a second order PDE that is given, which means the highest power is 2. Then you can write it in a general form. That is A dou square phi by dou x. This is a general form. Okay, whatever equation that I've written here is a general form. That is A dou square phi by dou x square plus B dou square phi by dou x dou y plus C dou square phi by dou y square plus D dou phi by dou x plus E dou phi by dou E plus F is equal to 0. Now you have certain these equations. So phi could be anything. It could be temperature or it could be any other variable, the concentration or whatever it is. And A, B, C, D are the coefficients of such terms. So what we have is if we have got one equation, we need to compare that equation with the standard model and identify what this A coefficient, B coefficient, C, D, E, F are there in our equation, whatever equation we are trying to solve. Once you've got this coefficients from the standard form by comparing your standard form to the equation that you have, you can calculate a term which is b square minus 4ac. For b square minus 4ac, if it is less than 0, we say that we are dealing with an elliptic PDE. And now b square minus 4ac is equal to 0, then we say that we have a parabolic PDE. Now b square minus 4ac is greater than 0, then we say that we have a hyperbolic PDE. What are this? So these basic divisions are based on how the solutions behave. It could be elliptic, parabolic, or hyperbolic in nature. So that will come into later. Now, what if we have first order PDEs? First order PDE is what we have just have dou by dou x, which means highest power on the equation is 1. Okay, there is no second order term. So in that case, the first order PDEs are basically having hyperbolic characteristics. So this is something general that you need to identify, then you need to like study by heart. So that is compare your second order PDE with the standard equation. So identify the coefficients A, B, C, D, E, F come by comparing your the standard form to the equation that you have. Then what you do is you calculate B square minus 4AC. If B square minus 4AC is less than 0, it is elliptic. If B square minus 4AC is equal to 0, it is parabolic behavior. And if b square minus 4ac is greater than 0, then we say here our system has hyperbolic characteristics. Then if we have first order PDEs, also we say that it has hyperbolic characteristics. So these are something we need to study. Now we'll see what kind of problems we have. So for example, I gave an example of road conduction, right? Road conduction, which is in transient condition, which means your temperature is varying with respect to time. So that is dou T by dou T. This is a transient part of it is equal to alpha times dou square T by dou Z square minus beta T minus Tk. So what you have is, do you have a term so first of all, you have to decide whether it is a for second order PDE. Yes, it's a second order PDE because the highest order is 2. So that is a second order PDE here because the highest order is 2. So because of that, we say that, okay, it's a second order PDE. Just a second. Yes, it's a second order PDE. Next, let us compare with the other equation. So what is A? A corresponds to the A corresponds to the coefficient of dou square phi by dou x square. Do I have that? Hmm, dou square phi by dou x square, like, no, either I can consider this instead of this, see, this x could be z, y, or z, okay, that you can vary. So either I consider my this term, dou square t by dou z square, falls here, or it is equivalent to this parameter. Okay, either it could be either the coefficient could be a or either the coefficient could be b. This you can replace it that there or here. So right now I'm considering there is only one variable. I'll consider this dou square phi by dou y square is there. Instead of y, we have z. Okay, I'm saying that okay, we don't have a term like this. So a coefficient is equal to 0. So what happens is your a coefficient is 0. And now what is b? B is when you have a mixed derivative of two positions, that is dou x and dou y. We don't have a term like that here. Do we have it? No. So because of that, we consider the coefficient b is equal to 0. Again, b is equal to 0. Now the term we have is dou square t by dou z square. So that I'm taking, okay, let here it will be. This x, y, z variables could change also. This is just a standard form, okay? So this I'm considering this term I have and the coefficient is equal to c. So this term is there and the coefficient c is nothing but alpha. Okay, so what you have to do is first beforehand you have to bring all this equation into one side. So what I do is I bring this right hand side equation towards the left hand side so that you get it equated to 0. Okay, that's what I first do. Then I write C is, so this alpha becomes minus alpha when I take it to the other side of the equation. So C is equal to minus alpha. Now I've got B, A, and C. Now what you do is I calculate this parameter, that is B square minus 4AC. B is equal to 0, A is equal to 0. So naturally B square minus 4AC is equal to 0. What kind of problem do I get? If it is equal to 0, I get it's a parabolic characteristics. So basically, when you have transient problems in diffusion or conduction problems, usually fall in this parabolic characteristics nature. Okay, you need to be able to compare the parameters and calculate b square minus 4ac and say where this problem is falling. Now imagine I have the conduction in a plate. So it's a conduction in a plate means there are like two dimensions, there are heat transfer that is happening along the x direction and along the z direction, whatever I explained in the previous slide. Now let us see what is this coefficients are. So here when I have two position coefficient, I'm considering one to be here, the other to be here. There is no mixed position, so this term is not there. Okay. So now what I do is dou square t by dou x square, the coefficient is 1. So I'm considering the coefficient of a is equal to 1. A is equal to 1. Do I have mixed terms? That is, do I have dou x, dou y? So in our case, it will be dou x, dou az. Do I have a mixed term like that? No, I don't have. So I say b is equal to 0. Now I have another position term, dou square t by dou z square, that too in second order. So that will be here. The coefficient is c. And here when I compare, c is equal to 1. So finally I get a is equal to 1, b is equal to 0, c is equal to 1. Now what will be my term b square minus 4ac? So now my term b square minus 4ac will be equal to, since b is equal to 0, you have minus 4 multiplied by 1 multiplied by 1. So it will be net will be minus 4, which is less than equal to 0, less than 0, right? So then what I have is I have an elliptic problem. So when b square minus 4ac is less than 0, what I have is an elliptic problem. And usually what kind of problem come in this? When we have boundary value problems in both directions. So here the both directions are x and z. Like that, when we have problems in different directions, then it could fall in the elliptic characteristics. Next is hyperbolic PDEs. Usually when we have equations like wave nature corresponding to wave nature, it usually falls under hyperbolic PDEs. And also first order PDEs also fall in the hyperbolic characteristics. I hope you understood. Any doubts? If you have any doubts, please to ask me because this understanding is very, very important as we move forward. The next part is how to, so I'm giving you some basic examples. The example is the Laplace equation that you see. So that is dou square t by dou x square plus dou square t by dou z square is equal to 0, which you have already seen in the previous example. Such Laplace equation falls in the elliptic PDEs. Okay, so please keep this in mind. At least it's important that you understand how to differentiate it, and at least keep in remember keep in your mind like one example for each. Now wave equation, that is hyperbolic. So wave equation is hyperbolic. You have this dou square u by dou t square is equal to c square dou square u by dou z square, dou x square. So this you can just compare it to the standard form and figure out if it is there. Uh, Hyperbolic is it is greater than or equal to 0, right? Hmm. I'll just tell you one thing before comparing, you will have to take this part of the equation to the other side. So it will become dou square u by dou t square minus c square dou square u by dou x square. Okay, so you don't have mixed terms. The coefficient of b will be 0. Then you have to look for a and c parameters. So a here and a is equal to 1. And C you get this is, so here this coefficient there is only one, and the C coefficient will be C square, that is minus C square when you take this other side. So now what you have, B square minus 4AC out of B is equal to 0. In minus 4AC it will be minus 4 multiplied by 1 multiplied by minus C square. So the net term what you get is 4C square. Since C square is always positive, what you get will be a positive answer, which means B square minus 4AC will be greater than 0. I'm just telling you in words. Do you need example once more? I'll just tell you. In this case, there are two second order terms, right? In the first second order term, here the coefficient is a. Sorry, just a second. So here the coefficient is a. So here you are bringing it to the other side. So this will become minus c square. This is your capital C. And b is equal to 0. So now what will be your b square minus 4ac? So b square minus 4ac will be minus 4 because b is equal to 0 multiplied by 1 multiplied by minus c square. So that will become what? Greater than 0? I'll just remove this part. Just a second. So what we have is it is greater than 0. It becomes 4c square, which is greater than 0. Hence it has a hyperbolic characteristics. Now coming into the heat equation, that is dou square t by dou t is equal to alpha dou square t by dou z square minus beta times t. Whatever we saw the conduction transient condition, such an equation is a parabolic characteristics. Right now, I've given you enough examples. I hope that is enough. Anybody having any doubts? Any doubts? Okay. If there are no doubts, let us move forward. So as I said earlier, so PDE has a very broad range of problems. There are different kinds of conditions. There are parabolic conditions, hyperbolic conditions, elliptic behavior. So there are like certain ways in which there is no one solution that fits for all. So that you'll understand when we are trying to solve PDEs. If you have to formulate the problem depending on what kind of PDEs you have, whether it's the first order PDE, whether it's the second order PDE. According to that, you have to formulate the problem properly. There are PDEs in space, for example, elliptic. That is, you saw it is in space only in the x direction and the z direction. There is no time dependence. Both are with respect to space. And there are PDEs in both time and space. That could be like hyperbolic. Usually it is hyperbolic or parabolic cases. Now, mathematically, how you're trying to solve is such a problem can be solved using these three methods, which is finite differencing, finite volume, and finite element. But here, we'll not be dealing with all three. We'll be just seeing an inbuilt MATLAB command for that. Now, also there is another method. Have a PDEs in both time and space, then there is something called as method of lines. So these four methods are the methods that we use to solve partial differential equation mathematically. That is, you're trying to equate the equations instead of using an inbuilt solver. If you're trying to solve it, these are the ways in which you are trying to solve your equation. Is that clear? Okay. So now what we have is, let us move forward and try to see how the equation is solved. So before this, I'll show you two MATLAB examples, and then we'll come into this equation part. Okay. So uh, just a second. Yeah. Let me just share MATLAB. Just give me a second. Just give me a second. Okay. Mm, I hope you can see the MATLAB, see the screen wherever I'm showing the MATLAB help center. Can you see this screen properly? Okay. I hope you can see it. And now what we have is, if we have like the parabolic or elliptic PDEs, usually here we are trying to solve a parabolic or elliptic PDEs. When you have such PDEs, you have like a inbuilt MATLAB solver which is called as PDEP. So this is an inbuilt MATLAB solver's name, which is PDEP. We'll be using this to solve a problem. Even in the recorded lecture, whatever problem that we are trying to solve, there also we have used this PDEP equation. Next is how to formulate this problem for the solver. So there is a very specific way you need to formulate this problem. We will see two examples so that the solution, what you have seen in the recorded lectures, becomes much easier for us to understand. So now this is a general syntax. That is, solution is equal to, you call that particular solver PDE, and there are certain input parameters that you're supposed to give. For example, EM is a value. It's a numerical value. It could be 0, 1, 2, like that. And PDE function, basically in the ODE solver, we have like an ODE function that you give. Like whatever equation that we are trying to solve, that you have to give here. IC function corresponds to the initial condition. Okay, initial condition, you put it in a function. So IC function corresponds to the initial condition function. BC function corresponds to the boundary conditions. So remember, in our case, we had one initial conditions and two boundary conditions. So that comes under this BC function. And then we have to have a mesh. That is, for example, if we had mathematical cases, I said finite volume, finite differences, right? So for all this finite doing this mathematical equations, we have to create a mesh size. For example, in ODE solver, we had a T-span, right? So here, since there is both position and then there is time, you have to have a mesh in the time, which is nothing but your time T-span, and mesh with respect to position, which is nothing but your X mesh. So we need discretization in both time and space. So that is corresponds to a discretization in space is corresponding to X mesh, and discretization in time is with respect to T-span. Okay, so now we'll see like what the description is. So if you want to get this page, you have to just type a MATLAB. You can just type this solver's name, PDEPE. It will give you several documentations, and this is the first documentation for that. Okay, so you'll see a lot of solved examples. So what I'll do is I'll just go to the solved examples. We can copy paste our commands in MATLAB and see if it is working okay. Okay, so now this is a command that we have. Solve is equal to PDE, M, PDE fund, IC fund, BC fund, XMesh, T-span. Solves a system of parabolic or elliptic PDEs with one spatial variable. That is, one spatial variable is with respect to X position coordinate and time T. At least one equation must be parabolic. And the scalar M represents the symmetry of the problem. That is, whether it is a slab, cylindrical, or spherical. That is, if you're trying to solve it using the Cartesian coordinate, there is a certain value of m. If you're trying to solve the equations using the cylindrical coordinates, then there's a particular value for m. If you're trying to solve using spherical coordinate system, then there is another value for m. So m represents what kind of coordinate system you're working with, whether it is a Cartesian coordinate system, cylindrical coordinate system, or a spherical coordinate system. Depending on that, m can be 0, 1, or 2. Okay, so that is what the m parameter is. Next is the equation being solved are coded in PDE fund, as I said earlier. Initial value is coded in IC fund, and boundary conditions are coded in BC fund. The ordinary differential equation ODEs resulting from discretization in space are integrated to obtain approximate solution at times defined in the T span. So this thing might be certain little bit difficult for you. I encourage you to understand how this finite difference method works for solving PDEs. Then what is generally happening is these PDEs you convert into several ODEs, okay, and that ODEs you try to solve. So that's how this mechanism is altogether. Now coming into a example. So let's first solve a simple example that we have here. So this is the equation that we are trying to solve right now. First, we'll try to solve this example and then we'll come back to the recorded lecture question. So here, try to solve a heat equation in cylindrical coordinates using PDE and plot the solution. So that is what is intended. So now first we have is in cylindrical coordinates with angular symmetry, the heat equation is. So this whole question is given us to us in cylindrical coordinates. So in cylindrical coordinates, du by dt is equal to 1 by x dou by dou x. In the bracket, you have x du by dx. Okay. Now what we have is we have given boundary conditions. In the boundary conditions, you have x varying from 0 to 1, position is varying from 0 to 1, and time is always greater than 0. The initial condition of the system. Initial condition means at any position, but at time t equal to 0, you're considering a Bessel function. So Bessel function is denoted by the capital J. You don't have to worry about Bessel function because in MATLAB, it's like you have a inbuilt command for getting Bessel function. Okay, you have to just mention what the Bessel function inside the bracket. There will be n x will be there. There's a n term associated with Bessel function. You have to just give that as an input to the inbuilt MATLAB Bessel function command. We'll see that, but just understand at one boundary condition, your first boundary condition is a Bessel function. And the boundary condition is like this, the first Bessel function J0 nx. And next is in the other boundary condition. So since the problem is in cylindrical coordinate, what will be the value of m? M, as I said earlier, if it's a Cartesian coordinate system, m is equal to 0, cylindrical coordinate system, m is equal to 1, and if it is a spherical coordinate system, m is equal to 2. So in our case, m is equal to 1. The PDE automatically enforces symmetry at the x is equal to 0 and the right boundary condition is. So this is the left boundary condition. So this is the initial condition, okay, at time t equal to 0. Right boundary condition, that is when the position at the first position, again, the Bessel function, we have a different kind of Bessel function that is denoting the boundary condition. And at the left boundary conditions. So just a second. Okay. Do you need a left boundary condition here? That is the first question that we need to ask. So look at here, whatever is in position. See, here you only have two conditions that is given to us. One is an initial condition and other is a position condition. That's it. Okay, so we have just two conditions here. There are no two boundary value problems. Okay, so because this is just dou by dou t and this is also dou by dou x. So we have here initial and boundary condition that is given. And this is an analytical solution for the problem. Okay, this is if you are trying to solve PDs, this is an analytical solution that you get. You can keep a note of this because if you want to compare your answer to the analytical solution, you can always do that. Now, before coding, you need to understand this general form. This is very, very important, understanding this general form. So, before you can code the equation, you need to rewrite the question that we have into the standard form. The standard format, that is PDE, PE, XX is like this. That is, you have a coefficient term C, which is a function of x, t, u, du by dx. And this term is multiplied to du by dt. And you have is equal to x raised to minus m, dou by dou x of x raised to m. Then there is a separate function f. And then there is a separate function plus s. Okay. So imagine that this is your question. Okay. In this is your question, this du by dt is here. Do we have a C parameter here? Like, do we have a term like this here? Let's like compare the standard thing to our question that we have. So du by dt is here. Okay. Do you have a parameter here? Like basically this term, do you have it? No. So basically you can take it C is equal to 0. Okay. Now after equal to, you have x raised to minus m. So what is when you compare, you get it m is equal to 1. Okay. Here m is equal to 1. Then you have dou by dou x of x raised to m. Again, m is equal to 1. It's not contradicting. Again, m is equal to 1 here. This m value is equal to 1. And instead of f x t u du by dx, you have this function, this one. You have this du by dx. Okay. This is your f. This is your f value. And do you have s? No. So this is equal to 0. S is also equal to 0. So I hope that part is clear. You have C is equal to 0, M is equal to 1, F is equal to du by dx, dou u by dou x, and S is equal to 0. So let's see, is this the same answer that those people also get in MATLAB? Just a second. M is equal to 1. Sorry, C is not 0. C is equal to 0. This will be negated. Du by M is equal to 1. C equal to 1. See here the coefficient is equal to 1. And f is nothing but dou u by dou x, and s is nothing, no term is there, so s is equal to 0. So we have extracted this by comparing our equation to the standard form what PDE is expected. So that part is done. Now what we have is you have to decide what are the variables. So x is your independent spatial variable, t is your independent time variable, okay? And u is the dependent variable that depends on both x and t. So this is a u is a dependent variable that is differentiated with respect to both x and time, position and time. Du by dx, sorry, du dx is there is a variable like this. Du dx is a partial spatial derivative. Understand? It's partial spatial derivative corresponding to dou u by dou x. Now you have certain outputs, f, c, and x that you get it from here. F, c, s are things that you get from here. Corresponds to the coefficient of standard PDE equation that are expected by PDE. These coefficients are coded in terms of input variables that are t, x, t, u, and du dx. So understand x is there, t is there, u is a dependent variable, and you have a new variable du dx, which is nothing but equal to your spatial derivative dou u by dou x. So now what we have is you have to have equations. That is PDPE expects certain inputs, right? So we'll go to that. PDPE expects m. So here you know m value is equal to 1. Now we have to code PDE fund. We need to code IC fund. We need to code BC fund. We need to define an X mesh and T span. So we'll go to each one by one. So what is PDE fund here? Let's go down. Okay, so this is your PDE fund. So instead of PDE fund, my name I'm using is heat CYL. Okay, this is the name I'm using for the PDE fund. It takes in these many inputs. So the inputs are this. Just keep in mind your inputs for this PDE function. X, your independent variable. Time, your other independent variable. U, which is your dependent variable, and du dx, which is nothing but the spatial derivative dou u by dou z. So these should be the inputs that it is taking. And then you have to mention what each parameter is. You have to mention what is C, F, and S is. So that will be the output of this. You take input all the variables, and output of this PDE function should be C, F, and S. Whatever we have found earlier. What is C? C is 1. What is F? Dou u by dou x. What is this in our case? That is nothing but this. Okay, these two terms are similar. So we write F is equal to du by du dx. F is equal to du dx, and S is equal to 0. End. So this forms your PDE fund, which I have named it as heat CYL. Is this clear? You should take inputs x, t, u, du, dx, and it should output C, F, and S. Any doubts? Okay. Now next is we need to have functions for initial conditions, and next the function for boundary conditions. So for the initial condition, if you remember, the equation was like this. At any position at time t equal to 0, you have the basal function j0 nx, where n is a value that has to be mentioned by the user, and n has been given to in the question also. So this is my heat IC is my initial conditions function that I'm naming. It takes in one variable, x. Why? Because time you know it is 0, right? So the only input that it takes is the position coordinate x. And in that I'm saying u0 is my initial condition output. Okay. So I write u0 is nothing but Bessel J is the inbuilt MATLAB function calling the Bessel function. And you have to say J0. 0 corresponds to this subscript and nx where n is already being given to your equation. So this is how you define the Bessel function. If you want to know more about it, you can just type help Bessel J. You'll get what's the syntax. So basically this part of the question, you code it like this, Bessel J. 0, comma, nx, where n is already defined. So for here initial condition, you take only the position as the position as the input because time it's already 0, and the output will be Bessel J nx. The equation you will code it like this. This equation directly you will code as initial condition. Is there any doubt in this part? Okay. If there is no doubt, we'll go to the next question. That is how to code the boundary condition. So the boundary condition is given like this: u1t j0n e raised to minus n square t. So for coding boundary condition, there is like a certain format. Okay. Since the problem is in symmetrical coordinate, m is equal to 1, PDE automatically enforce symmetry along x is equal to 0. So you don't need to specify the left boundary condition. Right? So that is because the problem is formulated like this. Now for the problems, you have boundary condition is your x could be having a boundary a to b. So we have a boundary condition either at a or either at b. So some cases you might have condition on both the boundaries, or in some cases you might only have value at one boundary, just like we saw right now. So in that case, we should have PDE has a standard function, okay, so that you can define both the right boundary condition and left boundary conditions properly. The standard form of boundary conditions expected by the solver is in this form. Okay, you have P xtu plus Q xt multiplied by the F, whatever F we got earlier. Okay, earlier equation we calculated what is C, F, and S. The same F comes here is equal to 0. Now we have to write our boundary condition in this format. So the boundary condition, what I do is equal to 0 is written, no? So I'll bring this side of the equation to the left-hand side and equate it to 0. Your equation is like this: u1t minus 1 comma t minus the Bessel function plus nothing is there. So I just put 0 comma something. Okay, there is plus, there is nothing there. So it's equating into 0. Now what I do is I compare this equation to the standard form. Okay, what is P? P is an equation that has x, t, and u as input. So that is this one. This is the P part. That is u 1 comma t minus j0 n e raised to minus n square t. So this whole thing is P for me. Okay, Q is multiplied to F. Do I have a term? Do I have a du by dx term? No, it's not there. So F is not there. So hence Q is equal to 0. This term is nothing but Q is equal to 0. Okay. So since that is understood, let me just clear these things. So now we'll have to carefully read this. So the boundary condition should have a signature function like this. So this is how the boundary condition is. Heat BC is equal to XL, XUL, XR, UR, T. These are the inputs. We'll understand what does each input mean. XL and UL corresponds to U and X at the left boundary. Okay, that is you have the left boundary position you have. That is XL, and the corresponding U value is the UL value. So this is position, and this is a corresponding U value. So in our case, it will be the corresponding concentration of Ca. U corresponds to concentration in our case. Okay. Now here, this is a right boundary position, and this is a right boundary value. And then you have time, which is the independent time variable. So this is how we call, this is a standard form. And then what is PL? Output of this function should be PL, QL, PR, QR. So what is P? P is a function that you get from here. So this is our P. And what is Q? Here in our case, Q is equal to 0. But PL means the P evaluated at the PL and QL corresponds to PL XTU and QL XTU. Whatever you get from here corresponding to the left boundary, that is x is equal to 0 in this problem. And PR, QR corresponds to these functions, whatever you get P and Q from here, but evaluated at the right boundary, that x is equal to 1. So now you write the function like this. Here my boundary value function, I'm calling it as heat PC. It takes an input, the left position, left value, right position, right value, and the independent variable time t. And it has to output P value evaluated at the left boundary, Q value evaluated at left boundary, PR at the right boundary, and QR at the right boundary. Okay, if you don't have any of these terms in the question, then automatically it will become 0. So I'm just telling for Bessel function n value is this, which is given to us by the user. Now, what is PL? PL is, do you have a left boundary condition? No, you only have a, do you have a left boundary condition? That is at What is the boundary condition that is given? No, you only have the right boundary condition. Okay, at position equal to 1 you have, at position equal to 0 you don't have anything. So basically your left boundary condition, you don't have P or Q. Both this P and Q is not there because we don't have a left boundary condition at all. So PL is equal to 0, QL is equal to 0. Now on the right boundary condition, that is at x is equal to 1, you have both PL and QL. So what is P? P is this part, right? So P is this part. You will just write uh, this is what this becomes U R, right? This is a right boundary U value. So U R minus this is Bessel J, Bessel 0, comma n. So this becomes Bessel 0, comma n multiplied by exponential minus n square t. See, this is what you code. This UR is what? UR is the right boundary condition U value. So that is this. Now Q, we have said that when we compared, you don't have any Q value. So automatically QR will also become 0. So this is the boundary condition. You have to ensure what this PL, QL, PR, and QR is there. If there is none of this are there, then automatically it becomes 0. If any of them are there, you have to appropriately write it in the function. So this is your P value. Q is not there, so automatically QL and QR became 0. Since you don't have the left boundary condition at all, your PL becomes 0, but your PR is there. So that is this equation. Any doubts so far? Okay. If there are no doubts, we will have to define the mesh first. So defining the mesh right now, I'm saying that my x value varies from 0 to 1. So that part I'm saying 0 to 1, I'm dividing into 25 equally spaced points. So that is my x mesh here. I use linspace command. And time also I'm telling it is going from 0 to 1 with 25 divisions. So this is my time span. Now I decide m is equal to 0. And this is the solution. This is the function that I use for calling my PDP. So sol is equal to PDP. I define m equal to 1. It's already to be defined here. Heat CYL, heat IC, and heat BC. I write the functions below. Then x and t is there, where x is the x mesh and t is the t span. Okay, don't confuse. These are not variables. This is corresponding to this arrays, two arrays. Now what I get is I get the solution. So the solution, how it will look like, we'll see. But understand that in solution, first you will have we'll have the positions, and then you'll have the time corresponding, and then you will have the U values. So for that, we'll just copy paste this value so that it is easier for you to understand. Let me just take Matlab. Okay. Let me just take Matlab. Um, you define the X mesh and you go back to this. You define your M and solution PDI. Just a second. Clear all points. Okay, solution PDI is there. Now I need to have the functions that is corresponding to it. So the functions, what I do is I'll just copy paste from here. This was my first function. Just a second. I can just maybe write as a separate function if I want to and save it. Automatically will take the name. Again, now I need the boundary function. Sorry, now I need the initial value function that comes from here. Copy paste. Again, substitute. Okay. And again, saving this function. Now I need the boundary value function. Going back, this is my boundary value function. Okay. Again, saving this. So this one, I'll just save this as example 1. Okay. Now what we do is we'll just run this function here. Okay. We have saved all the parameters. Now let me just run this. It's running. Yeah, the run is over. Now we'll just see what the solution looks like. See, solution might be a bit tricky, but if you need to extract the values, what you do is going back. See, so what you get is will be the solution will be a three dimension. Okay, there will be like all rows, columns will be there, and then there will be rows corresponds to the maybe position, and then you have corresponding to time, and then you have a, third dimension which is corresponding to your u value. So for extracting that, you will have to take your so basically you will get a 3D array solution where sol ijk approximates the kth solution of uk at evaluated at time ti and xj. So that is like this. I corresponds to time. The first dimension corresponds to time. Second dimension corresponds to the position, and the third dimension will give you the solution. So in our case, you will be getting. So if you look at the solution, you have to extract the solution. It will be like this. So I'll just run this only command here. You will get the u value. Okay. Why is a U value like this? U value is like this because there is like a variation in position and variation with respect to time. So it's a grid basically that you get at several grid points. You have gridded it with respect to time. We have gridded it with respect to the space. And then at every grid point, you get a U value corresponding to it. That is why it is a mesh like this. Okay. Now we'll see how to plot this. So surf TXU means surf will give you the grid of with respect to position, and this will give you grid with respect to time. And for the grid point, what the U value is, that also you will get. So just a second, we'll just surf is actually a MATLAB command that is used when you have a 3D surface. Okay, I'll just run this command, evaluate this command here. You'll be getting a surface like this. So this is an interactive MATLAB image. So for example, there are several icons that is given. This is for rotation. Okay, rotate 3D. I have selected this. Now I can rotate and see. So if you see here, this coordinate corresponds to the position. So here you can see position is varying from 0 to 1. And here you can see time is varying from 0 to 1. So if you take this point, this is a point where x is equal to 1, time equal to 1. And then you will get the corresponding value of u. So u is equal to 0 here. So if you take the next grid point, you will be getting the value here. It's difficult to understand what the values are. If you have a problem in understanding the values, one thing is you can just go to any of the pointers. See, then you will be getting x value corresponding to y value corresponding to z is your u value. Okay. So x value, y value, and you get the z corresponding to 0.01. Am I right here? Let me just go here and see. We'll see what the x and y axis is. So here x-axis is itself because it is 0.04, it is here. And here it is corresponds to 0.79. And the corresponding u value is 0.10281. So here you can see it is all, the u value is very close to 0.01. But here if I go, you will get the u value. Here it is denoted by capital Z as 0.768716. It's a higher value. So that is why there's a color gradation here. Blue means almost the similar value. As the color keeps on changing, you'll understand that the values are changing accordingly. And the U scale is being given here. If you are not able to read it properly, then you can go to any point, click on the graph, you will be getting the corresponding X, T, and your U value. Is this clear? This might be a bit tricky because the solution that you get is a three-dimensional vector. It is like a three meshes you get. One mesh is corresponding to your time, second mesh is corresponding to AX, and corresponding to each time and position coordinate, you will be getting a U value corresponding to it. So for extracting the solution, you have to just write solve. This is first dimension everything, second dimension everything, and third dimension you extract. Okay. So this gives you the solution for you. I hope this is clear. Any doubts? If not, let us go to the second equation, second example. So one more thing is there, if you want to plot what's the temperature change, okay, temperature change at x is equal to 0, then what you can do is you have the solution. Mm, In the solution, you have to just type time t is there, t that is if you want to plot the temporal thing, okay, whatever the question was asked in our example, if you want to plot the temporal, you have to just plot the t mesh, comma, solution, or comma, 1. So that is this. You get the temporal variation. You have on the x-axis, you have the time, and in y-axis, you get the all the solution with respect to 1. If you want, I'll just plot this one also. Just a second. Let me just close this. Otherwise, I'll just use it here so that you get it. Yeah. So now we are whatever you are plotting. Yeah, plotting solution. In the solution, you plot the all the temperature. The you need u at 0, right? U0 means you get the in the second coordinate, you just extract the first value. So that fixes u at 0. And then if you extract everything, you will be getting the temperature at all the positions with respect to time. Sorry, here the first one corresponds to time, second one corresponds to position. So here U0 means you have to fix the position. So this one corresponds to fixing the position, the first reading of position, that is at U0. Uh, so that is the first index given here. And then you get all your temporal variation, time variation. Okay. Any doubts? Okay. If you're not, let's go to the second question. Can you see the MATLAB screen? Just a second. We'll try to solve this question also, and then we'll come to the recorded lectures. Okay. So here what we're trying to solve is a single PDE equation. In single PDE, you have pi square dou u dou t. Dou u by dou t is equal to dou square u by dou x square. So here, this is one question that is similar to what we have in the recorded lectures. Here, with respect to time, it is first order, but with respect to position, it is second order. So it is a partial differential equation because it depends on both time and position. And your interval is x is varying from 0 to 1 and time is greater than 0 at time t equals 0. For example, since this is a first order with respect to time, you need one condition in time. So that is ux comma 0 is equal to sine pi x. So that is at any position at time t equal to 0, the initial condition is sine pi x. At how many boundary conditions do you need? Since it is second order, we need two boundary conditions. One is at the left boundary, that is at x is equal to 0. The other one is at the right boundary at x is equal to 1. So this is the value at x is equal to 0. You say at u 0 comma t is equal to 0. And this is your last boundary condition. The final boundary, this is the condition that you have. It is not in u, but you have it in dou u by dou x. Can you understand how to code this right now? So the first important part is you have to compare this equation to the standard form that PDE-PE takes. So that is the first thing to do. So how does the PDE-PE takes this equation? You have here the standard form like this, and this is the equation that we have. Okay, so now let's compare. Do we have dou u by dou t term? Yes, I have dou u by dou t term. What's the coefficient corresponding to it? It is pi square. So example, C is this term is nothing but your pi square. C is equal to pi square. Do you have a power to the x parameter? Here, x is nothing, x is not here. It's basically x raised to 0, that is 1. So here my power m is equal to 0. Okay, comparing this term and this term, I get m is equal to 0. Now what I have is, do I have a dou x by dou term like that? Yes. I can write this as dou by dou x of dou u by dou x. Okay. I can write it like that. So dou by dou x of dou u by dou x raised to 0 is nothing but 1 itself. Okay. So now what happens is x raised to m, again m is equal to 0. What is my f function? F function is nothing but dou u by dou x. Do you have a s term? No, I don't have an s term. That is nothing but 0 itself. Finally, this is what I get by comparing my equation to the standard PDE. I get m is equal to 0, c is nothing but pi square, and f is equal to dou u dou x, and s is equal to 0. Is this clear? After comparison, whatever you get, is this clear part? Any doubts? So if not, let us see what the variables are. Again, we have x as an independent spatial variable, t as an independent spatial variable, u is a dependent variable, du dx corresponds to dou u by dou x. And there are three outputs that your function should be giving you, the c, f, and s. Okay, the PDE function should give you c, f, and s as the outputs. So my PDE function I'm writing is like this, PDE ex1 PDE. This is my function name that I'm writing. And it should take in x, t, u, du, dx as the inputs. Okay, x, t, u, du, dx. Basically, the two independent variables, the dependent variable and du, dx, which is corresponding to dou u by dou x. Now I write c is equal to pi square. C is nothing but equal to pi square. F is equal to dou u by dou x. That is this, du, dx. I write f is equal to du, dx and s is equal to 0. Is this clear? Okay, once I have written this, now my PDE function is done. FC and FFS comes as an output to my PDE function. Now to write the initial boundary condition. Then I have to initial condition, then I have to write the boundary conditions. Now coming into the initial condition, as I said, time is fixed to be 0. Time is could be anything. So position is the input variable. So I take position as the input variable. Time is equal to 0. So position is the only thing that is ready. So with respect to position, I write u0 is equal to sine pi x. This one. U0 is equal to sine pi x. So, sorry. So you write u0 as output. So u0 as an output that is equal to sine pi x. This is an initial value function. I write PDEX1 IC. This is my initial condition. IC is corresponding to initial condition. You can give any other name also, that is completely fine. Now the boundary condition. So for the boundary conditions, you have to first write the boundary condition according to the standard format. And then you have to compare your equation to the standard format and try to find what each term is. So this is the standard format, right? P given by something, P xtu plus Q xt multiplied by F xtu dou u by dou x is equal to 0. So this is the standard condition. First, let us come to the left boundary. Okay, that is at x is equal to 0. You have written though u0 comma t is equal to, what is the condition? U0 comma t is 0. That is what we write. So let us rearrange that. U0 comma t can be written as U0 comma t is equal to 0. So that means you don't have this portion. Sorry. This portion can be written as u plus 0 du by dx comma 0 is equal to 0, right? So u is nothing but this. U0 comma t means your u value plus 0 multiplied by dou u by dou x is equal to 0. So if you compare, your p is nothing but u itself. Q is 0 because you don't have anything. F is nothing but du dx, which you already got from here, right? So you equate the functions like this. Now the coefficients are the p is nothing but u, q is equal to 0. Okay, for the left boundary condition. Now for the right boundary condition, this is the equation that has been given to us. Okay. Now what we do is we compare this with the standard form. Do we have a function corresponding to p x t u? Yes, that is nothing but pi e raised to minus t. Do we have a function corresponding to the coefficient of f? F is nothing but dou u by dou x. So this is f part. And coefficient should be multiplied to this f part. So that is nothing but 1. 1 is a coefficient. So pi e raised to minus t plus 1 times dou u by dou x. So here your p is nothing but pi e raised to minus t and q is equal to 1. Just read this carefully and let me know if there is any questions. How to write p and q in both the boundary conditions. Is that clear? I'll give you 1 minute. Just go through this. If you let me know if you have. I hope there are no doubts. So now we'll try to code this. Okay. So while coding this, this is how the format of the boundary condition is. It takes in the position at the left boundary, u value at the left boundary, position at the right boundary, and the value at the right boundary, and t your in the other independent variable. And p and q you get from the equation. PL and QL corresponds to the left boundary. PR and QR corresponds to the right boundary. I hope that is okay to you. Now this is a function that you write. Okay. XL, UL, XR, UR, and T are the inputs. So now you know for the left boundary condition, Q is automatically 0 and P is equal to UL because this you have evaluated for the left boundary, right? So PL is equal to UL, QL is equal to 0. Is that okay? Now you have to write the right boundary condition. The right boundary condition, PR is equal to pi e raised to minus t and UR is equal to 1. So exactly the same thing, right? PR is equal to pi exponential raised to minus t and QR is equal to 1. Okay. So now this boundary conditions also we have written. So PL, QL, PR, QR comes as an output. Now we create a mesh size. X mesh, I'm creating it for 20. And the time span I'm creating from 0 to 2, 5 grid I'll be making. M is equal to 0. I've got empty M equal to 0. Now I write solution PDE, PE, M. I call the function, I call the initial condition, I call the boundary condition. I'll give the X mesh and I give the T span. Now for the solution, as I told earlier, you should take the third dimension. So you write colon, comma 1. This will give you the solution matrix. And you can surface like this. That is X, T, and U. If you create a surface plot, a 3D plot, you will be getting a surface plot like this. Okay. Now, if you want to compare it with the true solution, this is the analytical solution for your problem. So what you can do is for the same X, T, you can write this, you can give this analytical solution directly here. And then you can plot the surface plot also. Is that clear? Now compare the solution, numerical analytical solution at the final value of t. At the final value of t means the u nth value. T, as I said earlier, in the U, first dimension corresponds to time, second dimension corresponds to the position. So the first dimension you give nth here so that it takes you to the last entry of the time and all the positions you get. So this you get the at time t equal to 2, which is basically the last time you get the what are the U values and you denote it by 0. And this is nothing but the exponential, this is nothing but the analytical equation that you have and you can plot it together. So now let us try to code this. Just give me a second. So I'll just copy paste this one into MATLAB. Let me just close all this. I'll write this as, save this as example. CLC. I'll save this as example 2. Okay. Now going back, let me just extract the, yeah. If you want, you can run this in online MATLAB also. That you can do, that's completely fine. And now you have to write all the functions. So functions, either you can write like one by one as I did earlier, or else what you can do is you can just take the whole function and you can write it after the script lines like you used to do before. This you can always do. Now we need to print the solutions also, right? So let me just go back. Where was my solution lines? Yeah, I have to extract this line. So, okay, just a second. Okay. Copy to MATLAB. Now I have to surf also. The surface also I have to get it. So that also I'll copy. Okay. And below is my functions. I've saved it. Now let me just run this code. You get the solution. This is a surface plot that you get. Okay. Your U value, you get 5 by 20 mesh from the solution. Okay. So this is a surface plot. Again, as I said earlier, this is an interactive plot. If you go to any of the positions, you will get what is your X value is, what your Y value is, and Z corresponds to your this dimension. Okay, 0.19719. So here you can say it's a low value. If I go here, you'll get a higher value. 0.996584. Is this clear? Any doubts? Okay. If no doubts are there, let's go to the question that we were discussing in the recorded sessions. I hope you can see the, yes. So now we have got a catalyst pilot equation like this. Dou Ca by dou T is equal to D dou square Ca by dou R square minus Ka. So the first thing is this question has been converted into a dimensionless equation where you rearrange this equations basically. That is Ca you divide by Cas, R you divided by capital R, and time instead of T you write a new variable T star. T star is nothing but T D by R square. And for alpha, what you do is you want an equation, you want a variable that is combining both K and D. So you write alpha equal to KR square by D. Okay, you can substitute this new things into this equation. And finally, so this ODE get converted into this. Dou Ca star by dou T star is equal to dou square Ca star by dou R star square minus alpha Ca star. This coming into this and this is the dimensionless quantities. I'm not like giving you step by step, but I hope that these things you will have done it in the other courses also in chemical engineering. So I hope you understand how to convert from this equation to this equation. Okay, so now we have combined both K and D into one. But remember that since we have changed the Ca to Ca star, R to R star, and T to T star, the conditions has to be varied accordingly. Okay, the boundary conditions will vary accordingly. Now we have to write boundary conditions with respect to R star and T star. Okay, that is very important. And now these will be the boundary conditions. Earlier in the boundary conditions, whatever the concentration of Ca at whatever position was zero. That will remain zero as such. Okay. Because whatever position of R you take, Ca is equal to zero. So automatically, whatever position of R star, Ca is zero, which makes Ca star zero. So your Ca star is equal to zero. Initial condition is fine. Now boundary condition is at whatever time at the position 0, Ca star is equal to Ca is equal to 0. Again, put Ca equal to 0 here. You get Ca star is equal to 0. Ca star is equal to 0. But your other boundary condition is at whatever this was a condition at whatever t and the surface. And at the surface, then you have concentration is equal to CAS. Do we have R here anymore? We have written the whole thing in terms of R star, where R star is nothing but R by R. So if we substitute here capital R, where R star becomes R by R, which is 1. So you write your equation like this, CA star for any time, and instead of capital R, you'll write 1 here. Okay, and that is equal to CAS. But CAS is what? If you substitute CA to be CAS here, you get CAS by CAS and CA star will become 1. So that is what you write 1. But one correction is there. Here T also should be T star. Okay. Is this clear? How did we convert this boundary conditions into another dimensionless quantities boundary conditions? Okay, once that part is clear, let us look into the problem statement. Sketch the temporal variation of the concentration profile in the catalyst pellet. Determine the diffusion effect of diffusion coefficient, rate coefficient, study the effect of time and space discretization, and solve them in spherical coordinate system. Okay, so this is how the different coordinate system works. This is a Cartesian coordinates. You have it in x, y, and z. In spherical coordinates, it will be in terms of r, theta, and phi. I hope you guys know already how to convert. So this is what we said. When we are working with Cartesian coordinate, your m is equal to 0. When you're working with cylindrical coordinates, m is equal to 1. And when you're working with spherical coordinates, m is equal to 2. This we've already seen in the PDE part. So now I'll quickly show you what the codes are. And then I hope you'll understand how the code has been written right now. Clear? Okay. CLC. I'll just close all this. Okay. Now what first we have is we have like several parameters here. Your capital R is given as 20 centimeter, right? Which has to be, there has to be, it was 2 centimeter, which has to be converted into meter because all other are in meter. So it becomes 0.02, which is a capital R, the radius of the catalyst pellet. CS, that is basically what is the concentration on the surface. It is 120 millimole per meter cube. And time, as I said earlier, it was given in so the time has to be converted. Okay, so no, sorry, the K has to be converted. K was given as 1. That has to be divided by 60. So that you'll get 1 divided by 60. Now, D is nothing but 0.15 times 0.001. Let me just check what your D parameter was once again. Yeah, D was 0.5 centimeter square inverse. You're converting into meter. Okay, you're converting this into meter. You're converting minute into second. So these are the things that we are doing. Uh, I think here I've made a mistake. It's 0.1. Yeah, I think now it will be correct. Okay. Again, checking. Let me just check the diffusion coefficient also once again. Diffusion coefficient is 120 millimole per meter cube. Meter cube inverse. Okay. I hope this is right. Now you have to just please check the units if I'm not making a mistake. Just confirm that once. Now you write alpha. Alpha we have already written that is as k r square by d. So since you have given all this parameter, you can calculate what is alpha from there. Now I am writing my T span. So X mesh, that is from 0 to 1. I'm creating a 50 mesh. And line the T span is from 0 to 1. I'm creating another 50 mesh. So just like we did in our previous example problems. Then I write M is equal to 0. Because whatever in my question is my M value 0. So how do we compare that? So this is the equation that, sorry, this is the, finally, this is the equation that we have. What is our M value? M value comes as the, just a second. So if you see here, okay, M value corresponds to the du by dt. Let's compare that. Okay, first du by dt here. What is the coefficient? Let me just annotate. Okay, do I have a u term here? Do we have a u term? Yes, u is equal to 1. Okay. Do I have another term was what? Sorry. U term is 1. X raised to minus m, x by dou x of something. So x raised to minus m. I don't have a term like that at all. So here x raised to minus m is not there. It can be written as dou by dou r times x raised to 0 dou by dou r of CA, just like we did in the second example. Compare it to that. So x raised to 0 it is. So m is equal to 0. And comparing it to the next one. Sorry, I think, yeah. Yes. And m is equal to 0. What is your f? So f has to be written as, okay, that is dou C A star by dou R. That is my f, dou C A star by dou R. In our case, it was dou U by dou X. Here it is dou C A star by dou R. That's the only difference. And we have a S parameter also this time. So earlier, whenever we had S, but now we have here S parameter is there. But your S is what? S is minus alpha CA star. Okay. So U is equal to 1, M is equal to 0, F is equal to dou CA by dou R, and your S is equal to minus alpha CA star. Sorry. I hope that is clear. Now going back to the MATLAB codes. Am I sharing MATLAB properly? Yeah. So now we have using PDE, M is equal to 0. This is your function for solving the PDE equation. This is the initial conditions. This is your boundary condition. This is your X mesh, and this is your T span. To extract a solution that will come to later. Now let us look at the PDE function. Okay. So here, there are like several equations that you have to give. Basically, you have to give x, t. Here it should be x, t, u, du, dx. That is the order in which you give. If you don't know what the other things are, you can just give a tilde sign. Otherwise, it is x, t, u, du, dx. Now here we know C is equal to 1. Did we declare that C is equal to 1? F is equal to dou CA star by dou R. So in our case, we are writing for C, concentration C, you are writing it as a new variable U. So that is why you are writing du dx, whatever you get it from here. And alpha, and your S, that is nothing but minus alpha CA star. Again, I said CA star, in this case, it is nothing but your U variable. So it will become minus alpha U. Here you have C, F, and S. Is this part clear? How did we equate this? Okay, next is the initial conditions. Initial conditions, if you remember, what will be the inputs? Inputs will be just X will be, the position will be the only input that you give. Okay, if there is no position given also, you can just type here X. But why we are using a tilde sign is because here you're getting your initial condition is 0. So whatever input of X you give, always it will be 0. It is not dependent on your X right now. So U0 is equal to 0 and U0 goes as an output for the initial condition. Is this clear? Okay. Now next is a boundary condition problem. In boundary condition, if you remember what all variables you should have XL, UL, XR, UR, and then you have what else was there? Initial conditions, positions was there, and I think it was T was a parameter, no? Let me just check. What should be the inputs? It should be XL, UL, XR, UR, and T. and the output should be PL, QL, PR, QR. So we have to compare this with a standard solution. So this is a standard form. Okay, let us compare what is P and QR. Okay, so for that, I think it is better that I compare with the what is given in the slides. So this is a standard format. So let's write the first boundary condition. CA T is comma 0. What is this? This is your UL, right? So nothing but UL is equal to 0. That's what you get. So what happens is UL equal to 0 means your P is nothing but UL. This part is not there. So basically you can write Q is equal to 0. So PL is equal to PL is equal to UL and you write Q is nothing but 0. That is your first boundary condition. Is that what we write in MATLAB? Let's compare. PL is equal to UL, right? And then you write QL is equal to 0 because that second term is not there at all in our case. Now coming into the right boundary condition. What is the right boundary condition? You have to equate. So this thing, this equation, one you have to bring it to the other side because your equation has to be written in a form, it is equating to 0. So here now this becomes your PR. That is PR becomes your UR minus 1. Compared to this, okay, PR becomes UR minus 1. Again, this part of the equation is not there, which makes your QR to be 0. Again, going to MATLAB, your PR is nothing but UR minus 1 and QR is equal to 0. Is this boundary conditions clear right now? Okay. So once you've written all the boundary conditions, initial conditions, and the PDE equation, I write the solution, find the solution from here. I extract the solution to be all the dimensions, and the last one is my gives me the solutions. And remember that this is a dimensionless concentration, right? So if I want to plot it, I have to plot it in the actual dimension. So that is X I convert into the R I convert back into capital R by multiplying it by R. Then this is my T given by alpha. This 100 is because I had converted the unit. Okay, centimeter to meter conversion is there. That is why it is like this. T I multiply by alpha and you have to multiply it by CS to bring back to the dimensional, to bring back to the other dimension. Okay, to convert the dimensionless concentration to the actual concentration with dimension. Again, I use a surf command. I'll run this for you. And this is the behavior that you get. Okay. This is your radial distance, your x, your time, and your concentration. Just like I said before, this is an interactive curve. So at several points, you'll be getting what this thing is. And this is your color bar. In the blue, when it is nearly blue, we have lower values ranging from 0 to 60. And when it is deep yellow, it is like 120 millimole per meter cube. That is a concentration. Okay. Another thing in this is you have to be very careful with the units here that you're using. Ensure that everything comes in the same unit system. Is this clear? Now the temporal variation, I hope you know how to do it because in the first example we did that. How to extract a certain time. Okay, I hope you know it. Can I move on to the second part? So moving on to the second part of the question was, just a second. Second part of the question was determine the effect of diffusion coefficient of rate constant and concentration profiles, whether a part of the pellet remains unutilized with some values of this parameter. So for that, you can use a for loop. Here I've just shown you an example of for loop. You can improve upon it, okay, depending on what you need. Here, what I'm doing is earlier RCS, that is all is fixed. D values, instead of having a fixed D value, I'm changing the D values to be this. And instead of having a different K value, I think I have to multiply with 0.1. I think the 0.1 is necessary. Just check for once, okay? Hmm. This K values also, I'm using different K values. X and T, that is X mesh and T span, it's the right thing. M again, it is 0. Now what I do is I loop over different D value and inside that I loop over different K values. For each combination of D and K values, I extract that and I calculate alphas. Now alpha is different, okay? For different d values, k values I take, different time I get different combination of alphas. Then everything remains the same. I use this, I solve, I call the PDE, I extract the solution, I do a surface plot, okay? Again, that's what happens. So all the sub equations, that is the PDE, fund, the initial conditions and the boundary conditions, everything remains the same. Okay. Just that I'm looping over different, I'm using two inner loops and I'm calculating for different D values and K values, finally forming different alpha values. Okay. So finally, your answer will look something like this. Okay. It can look different also depending on what kind of D and K values you use. So here the first plot is for a certain D value and certain K value. This is the behavior of concentration that I get with respect to radial distance. This is called as subplots. Okay. So instead of plotting different graphs and different figures, you can plot all the figures into a single plot. This is called a subplot in MATLAB. You can go check how to draw a subplot. Okay, I'm not discussing it here because of time constraints, but you can go back and check how to use subplots. So you get different behaviors. Uh, Maybe this D and K is not the region of interest. You can use appropriate D and K values. I've just shown you an example how to solve this question. Okay. Now I'm moving on to the next part, which is study the effect of time and space discretization on the time required for the solution of the problem. So as said in the recorded lectures, we have to use a tick-tock command. So I've written it here like this. So everything remains the same. Discretization has to be changed, right? So earlier in your discretization, you had used, what was the discretization? You used 550 grid points, both in space and both in time. Instead of that, instead of 50, I'm just changing my discretization to 20, 50, 100, 200. Even the time discretization, I'm changing into 20, 50, 100, 200. Again, like I did for the previous coefficients, right? The D and diffusion coefficient and the rate coefficient. I write it for different gridding. I loop over the different gridding and I write X and T now comes inside the loop. Okay, earlier X and T was outside the loop because the gridding was constant for whatever K and D parameters that I used. Now this comes inside. Now, like I did earlier, I call the solution. But the only thing you have to do is you have to use a tick and talk. Okay, this elapsed equal to talk is not necessary. What happens is this elapsed saves the time in that the variable. Okay, that's what it does. Or else you can just give tick and talk. And that is also fine. Okay, or I'll write elapsed equal to top. This can be also done. Then I save the elapsed value into a results vector. That's why I'm doing this. If you don't want that, you can just type tick and talk. What tick and talk does is when tick commands executed, it will calculate your clock for you. And when this line has been completed execution, it will stop it. And whatever time that is taken for this execution of this command will be saved in the variable elapsed. And this elapsed, I'm saving it in a different vector that is results. I'll just run and show to you what I'm doing here. Just everything remains the same, okay? NT values and X values, I'm plotting the results. Then I'm all the PDE, IC, and BC equations remains the same. Okay, I'm running this. Mhm. You get a plot like this. This is not necessary. You can plot it in different ways also. What I'm doing is I'm plotting NT and NX. I'm plotting it. This is not necessary. I think maybe this might be more useful for you, the results. Hmm. Okay, otherwise, I think this might be more easy for you to understand. When NX and NT is both 20 grids, the time taken is this much. Because what happens is more the grid points, it might take more time. Okay, but you have to understand whether the accuracy is increasing when you are increasing more the grid points. Sometimes, even if you take finer grid points, just the time will increase. There is no much change in the accuracy that will be happening. So it is very important that you need to understand that. So this is how the various times happens. Okay. You can go back to the recorded lectures to understand what the physical meaning of each of this is. I've just shown you the code. Okay. Because the code has not been explicitly given to you in the recorded sections. That is why I've just shown you the code how to do it. Is this clear? So the next part is a bit more tricky. I don't have the solution for this. I'm not giving you the code for that. So the thing is, the whole equation you have to change into spherical coordinate system. So when you do it in spherical coordinate system, by now we have done the cylindrical coordinate one example we did. I hope right now the only thing is you have to go to the chemical engineering basics and convert this into spherical coordinate system. Once you have done that, m will be equal to 2 for spherical coordinates. And then you can compare with the standard PDE, this one. Okay, standard PDE, you have to compare this equation with standard PDE. Now what happens? Your C and your all the S and F, all things are going to change when you convert into spherical coordinate system. And then you have to just compare and code it. I've shown you what the standard format is, how to write an example, and I've also shown you an example with the cylindrical coordinate system. So please take your time and try to do it in a spherical coordinate system, and you can compare the answers with your with whatever is given in the recording instructions. Is that clear? Any doubts? Okay. If no doubts, let me just show you some MCQ problems which will be helping you to solve your assignment questions. Just a second, and I'll give you 1 minute for each of you to think and give me the answer. Okay. Just give me a second. I hope you can see the MATLAB screen now. Just give me a second. No, just a second. So this is the first problem. I'll give you like 1 minute or something to solve the answer. Once you know the answer, please put that in the chat box, and I'll show you the answers afterwards. Just take 1 minute and put the answers in the chat box. What is the answer? The correct model equation for diffusion of reaction in spherical catalyst pellet is, we've already seen this, dou Ca by dou T is equal to d dou square Ca by dou R square minus Kca. This Kca has to come in the subscript, but I hope you guys understood. That is answer B. Next question. What is the answer? Spherical catalyst pellet has two independent variables, so that is both position and time, and one dependent variable, which is your catalyst concentration. So both option C is your answer. Now to the third question. How many initial and boundary conditions are required for solving the first question? That is the concentration variant in the catalyst, spherical catalyst. We know it's one initial condition because one corresponding to time and two boundary conditions corresponding to position. So that is answer B, one initial conditions and two boundary conditions. Next question. Which is the correct boundary conditions? Correct boundary condition, yeah, at whatever time t at x equal to 0, that is a left boundary condition. At whatever time t when x is equal to r, then that is a left boundary condition. That's the right boundary condition. Okay. So option D is your right answer. Coming to the next equation, next question. The model equation dou Ca by dou T equal to d dou square Ca by dou R square minus Kca is, yeah. Answers? It's a second order because there is a d square by dou r square term. And what is the power of it? It is 1. So it is a second order first degree PDE equation. The answer is option B. What is not a classification of what is the answer? We know parabolic, elliptic, and hyperbolic PDEs are there, but exponential PDEs we have not heard of it. So option C is not a classification of PDE. What will be the dimensionless time for the model equation? We have the model equation that is given. How did we write the time parameter t? What did we write time? We wrote time as Td by r square, right? That was your dimensionless time T star. So option A, what is the correct set of initial and boundary conditions in a dimensionless form of a PDE? That is first order in time and second order in space. The answer is option D. At any time, at a time t equals 0, at any position, we had a concentration to be 0. That is this one. And at time any time t, but at the center of the pellet, we had concentration to be 0. At the surface, the concentration was 1. That is CAS by CAS, you get it to be equal to 1. Is that clear? Now, what is display condition for the PDE? So Dirichlet condition for PDE is value of the function on the surface. Okay, we have seen what is Dirichlet Newman condition, Newman boundary condition, what is Robinson condition, all those conditions. We have seen it in the previous lecture. Here in PDEs, it refers to the value of the function on the surface. What is Newman condition for the PDE? So the answer is B, the normal derivative of the function on the surface. So we know that the Dirichlet condition means it's a function value, and Newman condition means it will be the derivative. So it's a normal derivative of the function on the surface if it is given, then we call it as a Newman boundary condition. How does a diffusion coefficient change the concentration profile across a radial direction at a constant k with time? What happens is when the diffusion coefficient changes, okay, when the concentration profile is the concentration profile across the radial direction for a constant k and time, there is a sudden drop for lower d. Lower d means there is like a competition between the diffusion and the rate of reaction. What happens is when diffusion coefficient is very low, the rate of reaction is what is dominating. So what happens? There will be a sudden decrease in the concentration of the element A. So that is sudden drop over for lower D. The answer C. Now, the next problem for large rate constants called diffusion coefficient, what happens? Choose a correct option. So the actual answer is A. What happens is when there is a small diffusion coefficient, the diffusion will not happen if the pore size is like very, very large. It will be most of the pore will be unutilized. So shorter pore length for catalyst pellet is desirable. That is option A. Now match the following. I'll give you 1 minute and then we'll discuss the answer. Any answer? So the option is the wave equation, we know it is hyperbolic behavior that we have already seen. So 3b, and the Laplace equation is elliptic. So that is 1a and 3b is your answer. Now the question, choose a correct option to complete the statement. A partial differential equation PDE contains one dependent variable, one independent variable and many dependent variables, or many independent variables and one dependent variable. Which is the answer? The answer is option C. If for a PDE equation, we'll have many independent variables. In our case, we had both position and time as independent variables and one dependent variable. So in this case, it was concentration, which is a dependent variable. So answer is option C. Now the question is, consider the following equation. Which of the statement describes this kind of an equation? So this refers to unsteady state because we have temperature variation with respect to time. Or you can say the transience heat condition also. So that's the last question. I hope it was useful for you. Please look at the PDE and compare your equation with the standard formats, and it will help you solve all the numerical questions. And the theory wise also, I've not gone into the analysis of the results. That you can go and see what the recorded lectures says. Because of time constraints, I've not gone into detail of the discussion of the answers. So I hope you have understood. Any doubts? If no doubts, I'll be ending the session. Thank you so much. Next Friday, 6 to 8, we'll be having the next lecture. Please do join. Thank you all.